Hi, my name is Yu metric number 189402, and today I'm going to talk about the application of the differential equation in the series RC circuit, specifically in charging a capacitor using a constant voltage. So I'm going to go through this very fast. This is the circuit diagram right here, and according to KVL, uh, the algebraic sum of all the voltages in a node should be 0, which gives us this equation right here. And then if we differentiate the equation with respect to t and divide it by r, we get something like this, and then we can solve it using the first order linear differential equation. This is the general equation right here, and then we can solve it first by getting the integrating factor, which is something like this, and then solve for the right hand side, the q. We get something like this. At t equals to 0, we get this right here, and in the end this is the final equation, which is I equals to v over r multiply with the exponent power of negative t over rc. So this is an non-homogeneous linear first order ordinary differential equation. Thank you.
Assalamualaikum and hi everyone. So I'm here today to represent the application of the differential equation. Firstly, I will introduce myself. My name is Intan Izzati and my metric number is 187245. So today I would like to pick one of an application of differential equation, which is falling object. It was a simplest application of differential equation in our daily life actually. So this application includes 4 variables, which is acceleration, velocity, height and time, and includes first order differential equation and second order differential equation. So an object is dropped from a height at time t equal to 0 if ht is the height of the object at time t and at is the acceleration and vt is the velocity. The relationship between these three variables, which is at equal to dv over dt and vt equal to dh over dt. For a falling object, at is a constant and is equal to the gravity, which means is equal to 9.8 meter per second. So combining these two differential equation, we can easily deduce this new equation, which is d square h over dt square equal to g, which means second order differential equation. We integrate these both sides and we obtain this dh over dt equal to gt plus v naught. Okay, we integrate one more time with respect to dt. Okay, this, okay, and we will get this ht equal to 1 over 2 gt squared plus v naught t plus h naught. Okay, this equation describes the height of the falling object from an initial height h naught at initial velocity v naught as a function of time. This as a function of time. Okay, that's all from me. Thank you.
Okay, this is my application. I choose exponential decay radioactive material. It's a first order differential equation. Let mt be the amount of a product that decrease with time, and the rate of decrease is proportional to amount m as follows. This equation is to obtain this equation where a is a non-zero constant. If we assume that m is mo at t0, then m0 is equal to ae0, which gives a equal to mo. The solution also can be written as like this. And lastly, assuming m0 is positive and since k is positive, m time is an decreasing exponential. The m divided by dt is negative k. M is also called an exponential decay model. That's all for me.
This is one
example of application of differential equation, I choose Newton's law of cooling as one of example of differential equation. It is a model that describes mathematically the change in temperature of an object in a given environment. So this is equation that I got regarding to the Newton's law of cooling. dt over dt equals to negative k bracket t minus te. Okay, this equation is the first order of differential equation because the differential equation is being differentiated regard to t only, and it is a linear non-homogeneous differential equation because the equation is not equals to 0 as you can see here, and it is ODE, which stands for ordinary differential equation because the denominator is only one unknown only. So this is how I got the equations. Dx over dt equals to negative kx. This is the main equation. Then you substitute x equals to t minus te into x here. Then you got here, and dx over dt equals to dt over dt. As you can see, here is my calculation. So that's it for today.
One of the example application of differential equation is the Newton's law of cooling. So basically what the Newton's law of cooling said is this equation. This equation is the rate of change time of the temperature is actually proportional to the difference between the temperature of the object, which is T, and the temperature of environment, which is indicated as TE. So let's x equal to T minus TE. So we get this equation. This equation is ODE. We classify it as ODE because the variable is same, which is T. So by using this variable, we get these differential equations dx over dt minus kx. So when we solve this equation, we get this equation x equal to ae minus kt. So when we have x, we already know that our x is equal to t minus te. So we substitute, we replace with a, so we get this equation. So we assume at time of 0, the temperature T is equal to TO. So our equation is TO minus TE is equal to A exponential. So this equation is equal to A minus TO minus TE. So by through this equation, we get the final result, which is this is the result. The result is T of bracket T is equal to TE plus TO minus TE exponential negative KT. This is linear ODE, and this equation shows the temperature of the object change in time. Thank you.